So, hi everyone. I'm gonna talk today about this project I'm working on together with Chaba and Free. So it's called The World Will Higgs from 6D. So this is Chaba, Free. Okay, so let me first start by briefly reviewing a few topics that I need for the rest of my talk. So let me start with composite Higgs. And so some of the authors here in the audience, so this goes back to the 80s by Kaplan and Georgi. This is 84, and the more recent revival is Agashi, Contino, and Pomerol. I think 2005. Right? So the idea is basically to sort of expand on the old Technicolor idea where the Higgs is just a composite object, but with basically trying to make the Higgs light by making it a pseudo Goldstone like the pions in QCD. And so the idea is that, as in Technicolor, you have a composite sector. So here, there's some global symmetry breaking, like the chiral symmetry breaking in QCD, where the simplest models have SO5 to SO4 breaking. And the Higgs is going to be a Goldstone of this breaking. And also we have all kinds of composite operators. Specifically, we can have composite fermions. And to complete that, we also have an outside elementary sector. Where we weakly gauge the standard model gauge group. And we have some elementary fermions. And now there's a mixing between these two, and so that mixing will generate basically a loop-induced potential for the Higgs, and also masses for the standard model fermions. And so the standard model fermions are going to be a mix between these elementary and these composite. And the main contribution to the Higgs is from the top loop, where top is mostly composite. All the other quarks and fermions are more elementary. And so, of course, so as I said, this weakly gauging and also this mixing breaks SO5 explicitly, so there's a potential for the Higgs, which has generically this form. So here, this F here is the scale of G of SO5 to SO4 breaking. A and B are order 1 parameters that you can tune. MT is the top partner mass. And GT is essentially parameterized the mixing between the two sectors. So GT is, naively it's just the top Yukawa, but it can, because of the specific form of the mixing, can be larger than the top Yukawa. It's, at minimum, it's the top Yukawa. And this is
dimensions what?
Yeah. And also let me square this. This doesn't matter for dimensions, but right. So this is the composite Higgs picture, but it's dual via ADS CFT to an extra-dimensional ADS model, which is just the Randall-Sandler model, and this also appeared in this paper originally. And so we have a metric which is just the ADS metric. And we have the Randall-Sandler scenario where we have the bulk of ADS, and we have two branes, the UV and the IR brane. And so now this breaking corresponds to putting SO5 in the bulk and breaking it on the IR brane. This weakly gauging corresponds to basically giving Neumann boundary conditions on the UV brane to everything, and then the fermions also live in the bulk, and so their localization tells you how composite they are. So this is all pretty well known. Let me move here. And so let me now do the second part of my introduction, which will be on the little Higgs, and specifically I'm just going to give an introduction to one of the first forms of little Higgs, which was dimensional deconstruction, or electroweak symmetry breaking via dimensional deconstruction. And this is what later has been known as little Higgs. And so I'm not going to talk about all the more elaborate models or more realistic models of little Higgs, but just the first appearance of this. This is basically Nima, Cohen, and Georgi in 2001. So the idea here is also pretty simple. So we have, they define basically a deconstruction of a 6D model, which looks like that in theory space. So there's sites and links. So this link goes all the way here, and this link goes all the way here. And there's symmetry here with SU3, but it doesn't really. So let me just tell you what, if you don't know what this picture means, it means that we have at each site a gauge group, which is defined at the site, and the links basically they correspond to a nonlinear realization of the breaking of the two gauge groups at the edges. So let me call this U and this is B. So U is basically e to the I pi over f. So there's essentially a pion in each link. And now the fact that we gauge this SU3, this eats up a combination of the pions at each site. And there's also one more, let me just start. There's the basic Lagrangian is just du squared with f squared, where f corresponds to basically the lattice spacing. And there's one more additional term, which is the plaquette operator. This is an operator that goes in loops at each loop that you can see like that. And basically it just multiplies all the u's at its ends, taking the trace. So the plaquette operator is basically ui v j plus 1, u dagger I, j, sorry, let me call this j plus 1, and v j dagger, and the trace of that. So this is some pretty well-known stuff, but let me just give you an aside on how to do these calculations and think about this very, very quickly. So this is probably well known, but I haven't seen this anywhere in literature, but you can think of this deconstruction as basically Kirchhoff rules. And it's very simple. There's this eats up a combination which is basically the sum of everything that goes in and goes out. So for all the mods that survive, the sum is 0. So this is like current conservation in a sense. So then we can define currents, and we know that everything that comes out is the same as whatever comes in. And this plaquette operator tells you that on all contractible loops, there's going to be, for each mode, the mode that goes all along the loop gets a mass. So for the zero modes, that sum is zero. So what that really means is that you can define potential up to non-contractible loops. So basically, each point has a potential, but if you go all around the extra dimension where you have a non-contractible loops, you get to a different point. But this is very similar to Kirchhoff's rule, so it's very...
What is the 5D picture for, or the 6D picture for the plaquettes?
I'm going to get there in a second.
Set this way up.
Is it visible if I write here? Can you see it? Okay. So then, let me first, I'll get to your question in a second. So let me first get to what are the surviving zero modes. So there are 2 zero modes in this picture. So let me call this is the modes. So one mode is just going up. So let me call that small u. Okay, so this is the mode. Okay, and so again you can see that. Let me first define this potential. So there's nothing going on between here, so it's the same potential at both these points. Then here's the same potential. Then going back to the same point, but after a non-contractible loop. So it's a different potential, and so on. And also you see that everything that comes in also comes out, so this also corresponds to my the first group. So then the second mode is the same, but going this direction, going right or left. So let me call that V. So these modes, again, this mode just for the group theory of this, everything is in the adjoint of SU3. So all these modes are basically adjoints, full adjoints of SU3. And so, again, you can see that this corresponds to everything that I said about deconstruction, but then there's one more thing, that the plaquette operator, basically there's one plaquette operator that you cannot remove just by defining the modes this way, and that plaquette operator is going to give you a tree-level quartic. So there's a quartic from the plaquette which basically corresponds to the commutator of u and v squared. So this is basically a quartic for these modes. And now, of course, it's possible to construct a model where you break this SU3 symmetry to an SU2 and you get just doublets and you lift the triplets. But I'm not going to care about that. I just want to understand this picture. And then let me get to the extra dimensional picture. So the extra dimensional picture of that is basically a torus. So the 6D picture. It's basically this is a torus, okay? So so this is a torus. So basically that's it with an SU3 gauge group defined in the bulk. So this corresponds to these. If you deconstruct it, you'll see these links appear. Basically, you can deconstruct like 4 points, and this is exactly this. And then what are these 2 modes? They're basically the 5th and the 6th component of the gauge field. So this U is basically A6, and the V is basically A5. And now where does the plaquette operator come from? So the plaquette operator is basically the field strength term, F squared. And more specifically, this commutator is basically coming from the A5, A6 commutator squared that lives inside of F5, 6 squared. So this is the extra dimensional picture. And so this concludes my introduction to composite and little Higgs, and let me get to our work. So what we have been trying to do is basically the following. So this this little Higgs picture already looks like an extra-dimensional picture. And also the composite Higgs story is also an extra-dimensional story. So the question is, can the two live together in a way? So what we are trying to do in our work is basically to construct a 6D warped composite Higgs. So basically, all we need to get the little Higgs is basically go to 6D. So maybe if we go to a warped 6D, we'll be able to have all the nice partial compositeness story, everything we understand from the composite Higgs, but in the little Higgs we also get a tree-level quartic and a more elaborate symmetry breaking structure. So let me just answer why. So why are we doing this? So first of all, this is going to be a new type of composite Higgs. So it hasn't been studied before. There might be some new phenomenology. We just don't know what it does, and the possibilities are pretty huge. So this is one thing.
This type of 6D construction plus space in 6D, I think.
That's true. That's true.
Do you have any new system or this warped one, or so why is the warped?
Well, because we want to localize things, in different places, and we want to understand this from also CFT ADS story, and we just want to see what we get. But also, I'll show you, like in hindsight, what does it really give you at the end of the day. So, so this is the first motivation. But the second motivation is that we might get an adjustable. So we might get an adjustable quartic. And so, first of all, in little Higgs, the quartic is order 1, so that is already being excluded. But the question is, maybe in our story we don't get, and I'll show you why it's actually true. But the question is, why is it good? So let me also explain this. Just do this.
Sorry, it's order 1 because of the commutator that we can.
Exactly, and because of the gauge coupling. The gauge coupling appears there, but you can't, what you get up at the end of the day is order 1 unless you tune it somehow. So I'm going to argue that having an adjustable quartic that is going to be small, like the quartic we actually have in the standard model, is good for composite Higgs models. So why is that? So just to remind you, there's a tuning. The tuning in composite Higgs basically comes from the following thing. So you would have thought that it is this. So you have the top loop, and we know what the contribution to the Higgs mass parameter is, and that is basically this. This is true in every model, naively, where m top is the top partner mass. And so the tuning should have scaled basically as this is should have. Let's see if there's another chunk.
A lot of chalk.
It's not the good chalk.
You brought your own.
No, there was some good chalk. So the tuning would have scaled as basically the top partner mass divided by 500 GeV squared. So this is what you would have thought that the quartic would be like in every model. This is just a model-independent statement. But really what happens is that the tuning in composite Higgs goes like, it's larger than f squared over v squared. So this is a model-dependent statement, but it's true that the most minimal thing you can get is this f squared over v squared. And let me just briefly tell you why is that true. So the reason why the tuning is typically worse than just looking at the Higgs mass parameter and just seeing what the top loop gives you is that the quartic is generated at the same level with the quadratic. So this is the problem. So why does this happen? Because basically the quartic and I mean you can see this in the potential I've already erased that so you can see that A and B are these order 1 parameters, but everything depends together on this choice. So if this hasn't happened, you might have said, well, I can play with GT, make it as small as possible, which is the top Yukawa, and then I would get this kind of tuning, but the problem is that the quartic you get will just be too small. And so you need to make GT larger so that you accommodate first the quartic, the correct quartic that we see, and then you get the tuning on A, which is stronger, and this is the dependence. So then you see that if I just add here an independent quartic and just set it to the correct value, this would make the tuning smaller. So
I want to understand parametrically the difference between these two. MT is G times F, no?
That's true.
And 500 is not so different from B. So they don't look so different. These two.
No, they don't. I mean, it's a question of, first of all, here M top is the bound you get just from direct searches. So you search for the T prime, you don't find it, you get the tuning. Here, F, the stronger bound comes from indirect bounds, specifically electroweak symmetry breaking, electroweak precision, and basically Higgs precision now. And these two are almost the same thing.
Okay.
So now you might say, well, I can play with my G star, make it as small as possible, and I basically get to the bound I get from the direct searches. Good. And actually, this is much more important in twinings, actually. So because we don't have a direct bound on top partners which are in that case neutral. Exactly, but we still have a bound from indirect searches. So so let me just tell you numerically, this in composite Higgs, this is like a factor of roughly 2, so it's not that great, but in the twin Higgs or in the composite twin Higgs, what you get is up to a factor of 4 or 5. So you basically erase all the tuning you have in the twin Higgs. This is nice, but I'm not going to talk about the twin Higgs today.
So the logic is you put a lambda, it's a composite Higgs.
Right.
You see a lambda, it comes from a breaking symmetry.
That's true.
The global symmetry. So what is the parametric then?
I'll show you in the 6D.
So it's a new source.
It's a new source because basically you now will have a 6D story, so nothing is a true PNGB anymore. So there's a breaking to the diagonal. I'm going to talk about this.
You have the tuning is F squared over squared. It's the opposite.
No. I mean, this is not true. This is just because of this specific form of the potential. I mean, you
Just
can.
because there is one scale, is that?
So think about.
And V is proportional to it. There's no more.
No, because there's also the scale of the top partners. So the question is, suppose you raise the ratio of the top partners to F.
Oh, input couplings. Okay.
Exactly.
So that
So
couplings in front.
that's true, but that coupling can be a large
Different
coupling.
couplings in the storm sector.
Exactly. So the question is, right, of course everything is proportional to F, that's true, but if you, the question is it proportional to F, which is what is bound by, as I said, electroweak data and Higgs data, or the direct searches on the top partner maps? What does it really scale with? So the tuning generically should scale just with the top partner mass, because this is what gives you back naturalness, right? But But as we see, most composite Higgs models are bound mostly by the indirect stretches, and this is why, because the potential is constrained to look this way.
But in most cases, the square over squared is smaller than MT over 550 because MT is of the order of G rho, let's say, times S.
That's true.
So this coincides with that, G rho is of order 2. So a relatively weak decoupled.
That's true. That's true. So
G rho is larger, as usual. This V square over F square is smaller than the other one.
that's true. That's
So
true.
this
So
view
the
is
game you can play here. No,
Let's say 6.
So
It's
the,
six.
that's true. But the
It's
game
not
you can,
really this which is limiting you. That one is limiting you much more.
so that's
This is just the cancellation you need to do in the quadratic term, in the X mass, in the A. So even putting aside the positive.
no. So that's true. That's true what you're saying. But the game you can play here is actually bringing G star down. So if you can play the game of bringing G star down,
Bring G star down, basically to agree.
well, up to a factor of roughly 2.
It's an order magnitude concept.
No. It is a parametric thing. It's true. But for instance, but the question, what we are trying to ask here is, what is the real bound on the tuning? How precise can you say that the tuning is bound by some experiment? So
Maybe we should allow him to continue.
yeah, let me just say the twin Higgs actually, in the twin Higgs story, this is actually very important. Here in the composite Higgs, you might squeeze a factor of 2, but in the composite twin Higgs, this is super important because now you can get basically a larger F without a tuning, and so you can evade all these bounds from Higgs data, for instance. So let me continue. This also. Okay.
So while you're okay,
Let's
Okay, so let me
There were
get
2
to-
points, so that was your list. So you started to put your goals and then you
right, just to these
Okay,
two.
very good.
So let me get to the model itself. So this has taken a few weeks to months of work, but let me just skip over that and let me get to the model. So this is the warp 6D model. So it's a pretty simple story. It's an ADS 5 cross S1. And so the metric is just the usual ADS 5 metric for the 5 components, and then just a flat dy. And the picture is the following thing. So it's orbifolded on a rectangle, and now we have, again, the G, which is SO5 symmetry here. And now the trick is, so let me call it like that. This is Y, the flat direction, and this is Z, the ADS direction. So this is the UV, now forebrain, and the IR forebrain. So if you're worried about the 6D calculations, I'm not going to do any of them. So I'm very quickly will go from this to 5D. But let me just finish with this. So now I break this G symmetry twice on the IR brane. Here to H, which is SO4, and here also to H, which is also SO4. And here I get my standard model gauge group, so this is corresponding to the weekly gauging. So just let me show you that there are 2 G mod H zero modes here. So let me get another chart. Okay, so let me give the spurion here of G mod H breaking, let me call that psi I R up, and this will be psi I R down. And here there's going to be some psi which breaks into the standard model on the U. So I can construct basically two Wilson lines. This one, let me call this up, and this one, let me call this down. And so the only two invariant objects I can, gauge invariant objects I can construct are basically this psi UV, this, let me call this W, Wilson line. W up, psi IR up, and the same with that. So these are the two modes. I'll call them H up and H down, and you can see them here. So we have made a few calculations in the 6D. We have solved the modes wave function in a specific gauge, and we also calculated the quartic exactly in 6D. And the good thing is that it completely corresponds to what I'm going to say next. Maybe here. No, but it's hard. So let me, from this, let me deconstruct this back into 5D. And so this is going to be a 5D RS model, which looks like that. There's a UV brane, there's an IR brane, and let me deconstruct this into two sites. So we have in the bulk G cross G symmetry, two sites, okay? Let me, maybe I'll write the sites. So there's a site, but you should think of the site as spanning all the extra dimension because it's a 5D site, so it's spanning all the way here. And so this will be SO5, and this is also SO5. And now, corresponding to this breaking, I'm going to break it here to SO4. And this one I'm going to break to SO4. This is unbroken here, and this breaks to the standard model SU2.
So we're deconstructing the 6 dimensions on two sides.
Two sites, exactly. So we call this the two-site RS. Now, the one component that's missing is breaking these two sides to the diagonal via link field. So this will be. And now the scale of the breaking is basically the F scale of this link field. This corresponds to the radius of the extra dimension with the gauge coupling in this way. And the Lagrangian you write is extremely simple. It's basically this thing. Let me not write this full picture. I'm just doing this F squared, the 5-dimensional F squared, and basically the link field squared with. Okay, this is the Lagrangian, so it's an extremely simple model. And so let me show you where the quartic.
Why wouldn't I have just started with RS and just done SO5 plus SO5?
No, you can do it.
Oh.
You can do it, it's not a problem, but the way we just got there is by going through this 6D detour into a 5D.
You're tormenting us through your.
Exactly.
No,
but
but we must do.
But it's true that Mima also started this way, where he started with a 6D but ended up with a 4D model. So we are doing the same. Right, so where's the quartic coming from? So quartic here is coming from basically, it goes like basically the F56 squared here. So here this corresponds to the covariant derivative in the fifth component of U. So basically this gives us a term which looks like that. where these are the two A5s, and pi squared. Okay, so this appears here. So, okay, so let's count the zero modes in this. To that I can take it higher up. Okay, so let's count the modes. So the modes are basically, let me work in the unitary gauge. So there's an axial broken combination, vector unbroken combination. So the vector is very easy. There's one mode in the vector combination. So it's the sum of the terms. There's another combination which is massive. So let me first think about the number of modes without the boundary conditions and then impose the boundary conditions. So the massive combination has two zero modes, like any massive scalar in 5D. So we have two modes in the axial. And now, so this is in the bulk. And now the question is, what happens after boundary conditions? So a very simple trick is that whenever you have a broken symmetry, that corresponds to Neumann, or actually no boundary condition for the A5. Whenever you have a gauge symmetry that is there, that corresponds to Dirichlet. So we basically have Neumann for everything here, but here it's unbroken, so that removes one combination. So we end up essentially, so there's basically Dirichlet on the UV brane from this. And so we have, after all of this, we have two modes. So where can I write? Let me write here. Okay, so we're gonna need a small quartic because the actual quartic is small. So that you will see will correspond to this scale of breaking being small. So this is where the adjustable comes in, but I'll get to this in a moment. But this gives us a very nice limit for approximating it, where if this breaking is small, we get basically that the solutions, so this for f being smaller than basically 1 over r, we get two solutions, which I will call A up, A5 up, so that's the upper, and it goes like Z, and there's A5 down, which also goes like Z in this particular gauge, so Z is the usual way the A5 goes, so this means the two A5s are basically decoupled in this limit, so that's nice. And then the quartic we get just by plugging these solutions, and specifically also expanding to second order so that we get the pion here being non-zero, we get the quartic which has the scaling. So I plug back the R6 from the F dependence, and then it has this particular form, which is this. So it has this particular pretty weird form, but that's actually the form of the quartic and little Higgs as well. And so our job here is done. So now the question is, so the question is, what is the size of that? How do we determine the size, and what size is phi? Right, I have two Higgs, so at the end of the day, for a realistic model, I'm going to need a specific form of potential. I'm going to get there in a second. But just, first of all, the first thing we have to get is that, that this quartic is somehow small, and we can play with this graph. So let me return back f, so this scales, this thing is basically this. So now, the question is, can I take f to be small? And the answer is yes, and it's slightly non-trivial, and this is where the ADS structure comes in. So suppose I have this f being small, I would expect I'll get new modes, and also I'll need a UV completion because this is just a nonlinear realization. But it turns out that because the breaking is in the bulk, the real scale of the breaking is above the KK scale. So let me just show you how. So suppose I have a zero mode. So all zero modes in ADS are flat in the correct choice, except for A5. But all the zero modes you can put are flat. And so now I'll give a flat mode a mass with this f. So even if f is very small, you might think, yeah, I'll now have a very light state. But because that state is flat and you're giving it a mass everywhere, the mass from the Planck brane actually dominates. And this mode is lifted to f, or fr, but times the actual Planck scale. So that mode, the zero mode, is gone. And so the only thing that can actually get a light mass, so that you are worried about, is something that lives on the IR and is massless, but there are no such things. All the KK modes, it's true that there's going to be an FR mass term for the KK modes, but they're already heavy. So this is why it's completely fine. You can take F to be as small as you want, and you'll get no problem with anything. Another way of saying that is that suppose I take this breaking and I UV complete it in a linear UV completion, and I'll just see when do I see the radial mode. So again, this breaking is flat, so the radial mode is also flat, and again it will get a mass which is Planck scale. So I'll never see the radial mode, zero mode. The only thing I'll ever see are the KK modes, and they are again higher than the KK scale, which is still defined by the ADS radius. So this is saying this in a brief way, but there's this can be formalized in a more formal way. But we will see that there are no new light states in the theory with the scale f generating them. So we can take it as light as we want. And the 6D picture is actually the question of stabilization. Can we stabilize an order 10 radius? And of course we can. It's not a problem. We already do this for this direction as well. So this is why it's an adjustable. It's technically natural to take this f to be small. You get no penalty from this. So this is nice. And then, of course, everything becomes a story of whether you can actually build a realistic model here. So let me just briefly say, I won't get to the actual model, and this is really new, so we're not sure we're doing everything right, but we think that we can construct a realistic model. But let me first just say what is required to have a realistic model. So you look at this weird potential.
So you
look
can
at this
pause. I'm still. What
Sure.
you're gonna just set here is still. This F that your fellow said. This is the same F. We didn't change notation. Here.
This is this F.
This is-
sorry.
Is that F that's above your
Let me
head?
call this F6. Okay.
Oh.
It's this F. I'm being slightly careless here.
Okay. Which is not F. as
No.
defined up
I still
there.
haven't defined this F at all.
Okay.
I'm sorry. Yes.
Okay.
This is the F, which is you can see here that because this mode is flat. This F is basically the scale of this G cross G breaking to the diagonal everywhere. Yeah.
Fine.
Right. I shouldn't change.
In the limit standard model slicato, did you slicato? You have only one mass. In the limit, did you goes away?
Yes, that's true. That's true. But you do change.
True Boston boson in the stone. Only one true Boston boson in the stone set. It will be pseudo when you put the standard model.
Yes, that's true. It's the difference of the two.
So I understand the quality. This must be coming from explicit breaking.
Yeah, but you do break it. You do break this explicitly because you break.
This is about physics. UV physics,
Explicit
explicit
collective.
breaking is UV physics. Now the rest are about physics. This is the CFT.
Yes, but the fact is that the CFT now breaks G cross G explicitly. If you look at the CFT, it's true that this is still weakly gauging, so you remove that, you remove 1-0 mode. It's true, but if you look at this here, you see that there's a G cross G breaking to the diagonal
Fine,
explicitly.
so there is, but in the limit that the standard model is not, the UV is not there, there is one gap with no quartic, with nothing. So I don't understand.
Let me think about this. So, but you are changing the boundary conditions in this way.
Oh.
So you're removing
Move the
that.
boundary, I want to understand the strong sector.
It's
This
true.
is the-
It's true
the
that-
above physics.
It's true because then if you just have one mode, this quartic disappears. So you can see this because it's a commutator quartic. So if it's a mode commuting with itself, it's 0.
So I don't have quartic.
So
Now I have to put the standard model and I have to generate quartic. So I don't see how this happens.
no, but again, so you're saying you remove.
Remove the UV, look at the above physics, that is the strong sector only. I want to understand what remains there. So there is a, as you said, okay, you impose from SO5, SO5, broken to from SO4, SO4. And now you are breaking the, inside the bar, inside the strong sector, it's broken to.
I don't really know how to take this limit actually in this case, because if you take the UV to 0, I don't know what happens to the radius of this of the other accelerometer. What is that size? Because you have
Look at the geometry, keep it, it's constant, no?
if I keep
Geometry there.
let me think about this. You just want to remove. I don't think to take this limit is trivial because the way I've written here, I have like R everywhere. So I need to redefine that in terms of basically R prime. So I think the quartic might really disappear in this limit, but also just because if you have one mode, there's no quartic. That's true. But
It's kind of confusing, as I said.
let me think.
The thing about the storm sector, I want to understand what you're doing in the storm sector, that is the bar and the infrared brain, this is storm sector. Now is the UV that is explicit breaking, no?
Mhm.
Breaking. So, okay.
But the question, okay, so what is your line of reasoning? You take the UV
I
to,
want to understand if there is one massless guy at the end of the day. And
you do have the other massless guy as well, but it's just decoupled. Right, is that, I mean,
understand,
because
this
you
guy
still
gets,
have-
no, because you take it continuously, the way you don't change the
number. Each
number.
other through the scalp. There's something in the storm sector or in the bound that make it to break it to the diagonals, no? There's no 2 S of 5 at the end of the day.
What would happen,
There's a link.
no, but what would happen in the usual RS if you take that limit, that mode? Will that mode?
You have also 5, also 4.
Ah, so that's true, so okay, so I understand what,
One
okay.
massless guy.
So you, no, so what, okay, so I understand.
There is no explicit breaking more on the standard model.
Right, so you're taking basically the UV to the, Alex. so you're taking the UV to 0 basically, to the ADS boundary, but then you still, I mean, you don't change the boundary conditions, so you still have these two modes, they're still there, because you have,
So this is what I want to understand. It's
you
one
still
massless
have
mode.
one boundary to one, but to one corner, and one boundary to the other corner, you still have that. This doesn't change.
So you have two modes,
You do have two modes, I mean.
two goldstones.
You do have two modes. The two goldstones are basically this, right? You can think
So
of,
they see each other at some point because you're putting this link.
and they see each other, yeah. They see each other through the link,
But
but
this quartic.
you add the link, so you add another mode, and that mode gets eaten together with the combination of these two, and one mode, two modes still remain, so this is, the counting here is pretty easy. And from the 6D picture, it's very simple to see that this is the case, right? Because you have two modes which are basically Wilson lines from two ends of the breaking, right? So you can have this to this, or this to the upper one. And so there are two modes here. And I mean, I didn't understand you correctly the first time. So of course there are two modes, even if you take the boundary to infinity. Because what will happen is that, you see, you might think, yeah, I break this, so there's nothing. But by breaking, I also add another degree of freedom. And when I break this, I get basically two combinations are, so one combination here is eaten, and the other combination here is eaten, but there are, let me think of this exactly. So, but there's still, you still have the Neumann boundary conditions here, so you might do this and you will see that there are two modes that has to be true. I mean, also, you can think of the 4D deconstruction of this, right? So, let me briefly say what it is, right? So the 4D deconstruction of this is basically something that comes out of here and goes here, but doesn't arrive here. And also something that comes from here and goes here. I mean, if I think of this as having many sides here. So there's a mode that goes through these things. It does have some component here, but, and there's one that goes all the way here. I mean, this is very similar to what you get in, so no, there are definitely two modes here. And they see each other through the fact that the axial symmetry is broken. So that is why we do get the chord.
So the spontaneous breaking is also 5 to also 5 first.
The
Also
spontaneous,
5 to also 4. You understand the idea? The spontaneous breaking, it's spontaneous. That is what.
I mean, it's in the bulk, so the CFT of that is actually
Spontaneous in bulk
is
spontaneous.
explicit.
No, spontaneous.
Well,
Bulk is the strong shape.
but it's also happening near the UV, so it's happening everywhere in the same way. So it's actually what it does is basically suppose you have this simple story where you have a U1 and it's broken in the bulk. Okay, sure. Well, I'm almost done, so it's fine anyway.
Realistic models are also very.
Exactly. So let me just tell you. But I mean, we do care about that. It's a long story, and I won't go there because to actually build the realistic models, you need to realize the quarks, and specifically the top in this picture. We do have a way to realize that, and you need to build the usual Higgs potential from loop corrections.
So with the Higgs, you typically need a second plaquette in order to lift the flat direction.
Yes, that's true. That's true. So here, exactly. So let me get to the flat direction. So so there you can see from this that there's a flat direction, which is basically either h up is equal to 0. Either h up goes to 0 or h down goes to 0. So if you give mass just to one of these two, you don't get anything because you're giving a mass in the direction that is flat. So you have to give a mass to a specific combination. And the usual way we do this is that we write these combinations. And so these two combinations do have a coordinate. And so if you give a mass to these guys, you lift the flat direction, or to one of them. And so to have a realistic model, that basically what we need. And to have a good realistic model is that we need to have, say, a negative mass squared for H1, a positive large mass squared for MH2, and preferably no mass to H1, H2. And so if we do this, we get that only H1 gets a web, so it's an inert Higgs doublet. The phenomenology is much simpler. And so this is what we actually do with our embedding of fermions, but I won't have time to tell you about this. So, thank you.
Okay, but to get these, they have to break some symmetry.
Exactly. exactly,
No,
exactly. So the thing is that this is now achieved by the, not by a plaquette like in the original little Higgs, but by the fermion contribution.
Most questions. Yes, no, you.
So if you generalize your Fs or the radii into, like in the 6D picture, as actually trying to stabilize the dynamic, radii, would the mixture between these modes cause this hierarchy to sort of fall back?
What hierarchy? No, I didn't.
The hierarchy between your little F6 and,
This hierarchy.
yeah.
No, it's a
That's-
question. So if you want to stabilize it, the simple way you can stabilize it is just pinch it on the UV brane essentially, but with a smaller master, and so it's pretty large, like Goldberger Wise. And then because just by making this Goldberger Wise scalar flat in the extra dimension, it's going to keep the same radius everywhere. So I don't think, I don't think it's hard to make the 6 dimension slightly larger than the small, the 5U. And essentially in the Goldberger Wise potential, you already have small numbers, so I don't think you'll get large corrections, if that is your question.
Yeah. Okay.
But we haven't really considered the stabilization. But let me just say that, at least in terms of phenomenology, if you look at this two-site model and you take it on its own terms, you might think you need a UV completion at the scale of 4 pi f6, but that's actually not true. You need a UV completion beyond the KK scale, and so that is fine. And again, that's because you break it everywhere. So f6 is actually not the warped down f6, but it's the large f6, the Planck scale f6.
So what are the main phenomenological differences you expect with respect to the standard composite scenario?
So one thing is that you now have KK modes that, supposing these, the axial and the vector components, and whatever you put in these groups that will have that, that if you take f6 to 0, you get two modes with the same mass. But now, once you give it a small f6 and you need a small f6, you get a very close KK modes to each other. So that's one thing. And if you do a 4-site or many sites, you'll get that there are many modes that sit right on top of each other with a gap, and then a very small mass difference. So that is one. Then, of course, the other is that you would expect to probe this model not via indirect searches, but just direct searches of top partners, because you can evade indirect searches this way, because you can always play with this f to m top partner ratio up to, of course, it's an order 1 factor. But you would expect to first see it in the top partner searches.
So are you also doing SO8? How,
It's a good question.
how much
Yes,
stamina do you have?
Yes, but we haven't made much progress in the twin Higgs direction. We will try to think about it, but in the twin Higgs, it's where we gain the most.
Yeah.
And it's interesting there. But we first wanted to write down the model, see that everything makes sense, see that we can get a realistic composite Higgs model. And I just have to say that getting a realistic composite Higgs model is probably not the same as getting a realistic twin Higgs model, and we're going to need some other tricks there. But
But just to point out what the competition to this idea, to adding the tree-level quartic is, to address this v squared over f squared problem, which is not a big problem, but it's a little hierarchy problem.
yeah,
The competition
it's
is a
little
tadpole.
hierarchy. Twice little hierarchy.
Hmm?
It's the little hierarchy
A
problem.
little, yeah, a very little hierarchy. So the competition is a tadpole.
Exactly.
So that also separates the.
Right. It does the same thing. It separates the vev from the mass,
Yeah.
essentially. But the
Adam
tadpole.
wrote a nice paper.
Right. You have a paper on that, but I'm actually not sure that if you write this in a composite Higgs model, I'm not sure you won't, because you need to get a tackle, you need to break some symmetry at a low scale. So there are complications. You do have that in your paper. I mean, probably you can evade that, but it's also some tricky, there's some tricky phenomenology there.
It'll be ruled out sometime soon.
Yeah.
Okay, let's thank Michael again.